Oh, okay, so let's start. So today we're going to talk about the system that I mentioned last time that's kind of interesting because it tests a bunch of things. So here you have a heat conducting table, let's say, and on this table we have a stand, and the stand here holds a rod that can pivot. So here is the pivoting rod. Ooh, I drew that pretty well. Okay, and so the pivot point, is right there. And then we have a bunch of cylinders with pistons here. So let me draw one here. And here's another cylinder. And then here's another cylinder. And then the pistons are in here. And then there are rods that are connected to this rod, so these points can pivot. Okay, and each one of these is filled, let's say, with a gas. Okay, so you see the picture there. So the thermal conductivity basically connects them all thermally. So they're not actually touching each other, but they're thermally connected. And they're mechanically connected because of the pivot point here. If one of them goes up, the other one on the other side has to go down. It's going to be opposing, okay? And then the distances are picked such that this distance is 1 unit, this distance is 1 unit, and this distance is 3 units. And I think I labeled this opposite to the way it is in the book. I call this number 1, system number 2, system number 3. I just did it in the order of the cylinders and the pistons. But I think in the book they call the middle one 1 instead of 2. But it doesn't matter what you call it. Okay. And so what we like to do is to see what happens to the volumes and the temperatures of those 3 cylinders. Okay. And and in particular, we want to calculate the equilibrium condition. Okay. So remember, in equilibrium, delta S equals 0. Okay, there's no entropy change. So what we need to do is to calculate delta S. Let me just write it as ds here. So what I do is I recall that S is a function of u, v, and n, and I'm going to have to differentiate with respect to those parameters. But I'm going to also use the fact that this n is a constant. Okay? So let's go through this. So there's a lot of derivatives to do here. Okay? So there's a partial of s with respect to u. And then I guess I should label things carefully here. So remember that we're going to have some other conditions here. So the entropy is going to be S1 plus S2 plus S3 because the entropy is additive. U, the total energy, is going to be S1 plus, oops, not S, U1 plus U2 plus U3. Okay. And we know that the volumes are going to be connected with each other. And in particular, we know that the change in volume 1 is going to be twice the change in volume 2 because of the lever arm. Okay? And, and we know this because the distance that the piston travels times the area of the piston is the volume, and the volumes are going to be all the same. Okay? So I'm sorry, the areas of the pistons are all the same on all these. Okay? And then the other condition is going to be that dV3 is going to be minus 3. Actually, let me move this over a little bit. Minus 3 dV2. Okay. Does that make sense?
Oh, it's a distance.
Hey, do you have 2 1s instead of a 1, 2, and 3 on the diagram?
So you're talking about these over here?
Yeah.
Yeah, those are distances.
Okay, you're saying they're the same.
Yeah, so those two distances are the same from each other. Okay, so I guess another way I could have done it, I could have said, oh, this distance right here, is 2 units. Okay, but yeah, but those are equally spaced. Okay, good. So, oh, and I've already started mixing. I have to be very careful here. I'm trying to use the notation of the book, and remember, in the notation of the book, the system is labeled with a superscript. So the change in 1 is twice the change in 2, and the change in 3 is twice the change in 2. Okay, sorry about that. And if I drift from my notation here, you can remind me so that I don't continue to write it down incorrectly. So I'll have system 1 here, du system 1, plus the partial of system 2's entropy with respect to its energy, plus the partial S3 with respect to U3, du3, plus the partial S1 with respect to V1, dV1, plus the partial S2 with respect to V2, dV2, plus the partial of S3 with respect to V3, dV3. And all those have to add up to 0 if the entropy is to be stationary. Okay. So now let's put in all these different relationships. So from the energy conservation, we can see that there's one equation. And when I differentiate that, what I can then say is that du3 is going to be minus du1 minus du2. Okay. So whatever the change in energy in 3 is, since the 3 have to add up to a constant, we're going to have minus du1 minus du2. Okay, does that make sense? Okay. Okay, good. Every time I see David leaning forward, I think you're going to hit the space bar, so I wait a little bit. So that's good that you gave me the thumbs up, because I don't want to waste time waiting for you. Okay, and then the first term here is going to be 1 over T1, because remember, that's what the derivative of the entropy is with respect to energy. So this one is going to be 1 over T2, and then this thing is going to be 1 over T3. Okay? And then finally, we put in the condition for the volumes. And so what we find is that this one is going to be 2 dV2. And then this one is going to be minus 3 dV2, right? And then this is going to be pressure 1 divided by temperature 1. This is going to be pressure 2 divided by temperature 2. And then this is pressure 3 divided by temperature 3. Okay? So hopefully I'm doing all my notation properly. So now I'm going to collect like terms. Okay? And do you, I don't know if this is something people do anymore, but when my son was in high school, they always talk like, well, let's go to the store, let's do this. They would use the term like, okay? And then he was doing an algebra problem. He says, Dad, what do they mean when they say collect like terms? Okay, so every time I say this, I always think of that question. Okay, so let's look at the, so we're going to collect the like terms. And so we're going to get 1 over T1, and this term here and this term here are going to combine. We're going to get 1 over T2 du1 plus, and then the middle thing here we have 1 over T2, and then we're going to get minus 1 over, oh, and I already made a mistake here, but let me just finish writing this. So in this first term, this is a T3, okay? Because this du1 we got from way over here, okay? Good. And then, so that's all we have for the energy terms, okay? We just have those two. And then for the pressure terms, we're going to get pressure 1 over temperature 1. And then that's going to be written in terms of, let me see. Yeah. So we're going to get pressure 1 over temperature 1, and there's going to be a 2 here. Then we're going to get plus pressure 2 over temperature 2 from the second term here. So we did the first term already. And then this final term is going to be minus 3 pressure 3 over temperature 3 all times dV2. Okay? So before I go on, since this is so complicated, I wanted to make sure you all agree. Does that look right? Okay. I think you're slowly agreeing with me here. Okay, so yeah.
So is this the second part, the second line, is that ds or is that plus the previous part?
You mean this line here?
Yeah.
Yeah, so this line here is from these last 3 terms.
Okay.
You forgot to put a plus sign before it.
Yeah.
Oh, here. Oh, I see what you're saying. Okay, yeah, you're right. Yeah.
I don't know that.
Yeah. Good. Yeah. It's not that it's equal to that. Yeah. It's good to know what it is. So that's a good comment. Okay. So basically, we're going to assume that all these differentials are independent. So these are all independent because we've already put in the dependencies of how the v's depend on each other and how the u's depend on each other. So now what's left over is independent, and because the sum of these things has to equal 0, I'll put it up here, that means each term has to be equal 0. Okay? And to make a long story short, this first one will tell us that T1 equals T3. The second term is going to tell us that T2 equals T3. And by transitivity, we have T1 equals T3. So they're all equal. Okay? And let's call all that temperature just T, okay? Because it's easier to write. Now that we have that, this last term, when we set to 0, we're going to get 2 P1 plus P2 minus 3 P3 times, well, actually I don't need a time since these are independent. That has to be equal to 0. Okay? So we're actually done the problem. It seems like we're not done because it looks like we still have an equation left. But actually, we are done. And one of the things we can do is let's take this last equation, and I'll do this in red so you can see what we're doing. Let's multiply by the area of the piston. Okay?
What's this math you did here?
Did I screw something up?
Well, you just put everything over T instead of the individuals?
Well, remember, because all the T's are equal in the previous line.
Oh, okay. Got it.
Okay, good. All right. You had me worried there. I thought, oh, my goodness. Okay. So I'm going to multiply that by A. And then let me multiply by some L. And let's just assume that when I say 1 here, I mean, L, 3L. Okay? Because it wasn't important in the other place. So if I do that multiplication, what you'll see is that this expression looks like 2L force 1 plus L force 2 minus 3L force 3. Okay? So pressure times area is force, okay? Now, what kind of equation does this look like from mechanics? What quantity is distance times force? Does that look familiar? Okay. Do an air symbol if you don't want to talk. Okay, talk.
Work, or that's a W, I guess.
Okay, well, it does have units of work, but it's also torque.
Oh, yeah.
Okay, because remember, torque and work have the same units. Good, good.
Mhm.
So this is telling us that the clockwise torques have to balance out the counterclockwise torques. And so here you can see how a thermodynamics problem really gives us the mechanical result. So it's all working beautifully. Okay, good. So everything is as it should be. Okay. So in a sense, just to write down the conclusion here, is that this is giving us the equilibrium torques. And the torques are due to the gases. So you could imagine if you did something else like isolated them so that they no longer can transmit heat to each other, then all their temperatures could be different. You could, set the temperatures to be different, all the torques would be different, and there'd be a different equation to balance this out. Okay. All right, good. So that's the end of that. And then the next topic we're going to talk about is matter flow. So if you think about it, we've already talked about heat flow, and here we've talked about how the torques can balance out. And now we're going to set up our system where we have a box like we had before, and then we'll have our piston inside. But now the piston is not going to be able to move. When that happens, let me draw the piston out here. Then I'll move it inside. Okay, so we have this piston here, a non-movable one. And what we'll do is we will make the piston porous. So there's going to be little holes through it to allow gas particles to go through. So this piston will allow gas particles to flow. Okay, so we're going to call this part right here system 1. Here we're going to call that system 2. So the particles can flow and heat can flow. So we're going to let gas particles to flow, and 2, we're going to allow heat to flow. Okay, so now that you're such experts, we can just write down the change in entropy, set it equal to 0 really quickly. Okay, because we know we're going to get the derivative of the entropy of system 1 with respect to U1 du1 plus change in entropy with respect to U2 du2 plus partial entropy with respect to N1 dN1 plus partial S2 with respect to U2 dN2, and I can see I made a mistake here. This should be a 2, like that, okay? And then as before, we're going to call this thing 1 over T1. We're going to call this thing 1 over T2, okay? And then we're going to call this minus mu1 over T1, because remember that the term, mu(n) at the end with the energy, okay? If we write the energy this way, we get that, but with the entropy, we get minus u over T. This is a mu over Tn, okay? So that's minus mu1 over T1. Okay, so that's now something new that we haven't varied before. But then here we're going to have minus U2 over T2. Okay, so just like before, now we're going to collect the like terms, and we're going to use again the condition that N1 plus N2 equals N as a constant, and U1 plus U2 equals the total energy. That's a constant. And when we put those two conditions together, we're going to get 0 equals 1 over T1 minus 1 over T2 du2 plus, well, I guess I should just say minus here. Actually, it doesn't matter how I do it. But let me just say minus. Then here I'll get 1 over T1 minus 1 over, oh, not T, mu. The T is there, but I forgot the mu. So you have mu1, mu2, du1. So you have to be careful when you go fast to sometimes write the wrong thing, which I did twice. Okay, is that okay now? Good. All right, and so again, because these two terms are independent, okay, then this has to be equal to 0, and this has to be equal to 0. So that first term here gives us T1 equals T2, and let me just call that T, and then that makes the last expression be mu1 minus mu2 over T equals 0, and so that means that mu1 equals mu2. Okay, so you can see a pattern here. Okay, when you're reaching equilibrium, the temperatures on both sides have to be the same. Okay, when you're in equilibrium, the chemical potentials have to be the same on both sides. Okay, now the one thing that's kind of funny about all of this is that temperature and pressure are actually very common intensive parameters that we're familiar with. We can feel the heat coming out of the oven, so we sense that temperature. We sense pressure, right? Squeeze your head, you'll feel the pressure, right? So we have a good, do the experiment. So we have a good feeling about what these things mean. But the chemical potential is something that we don't have a good feeling for, okay? And so this is probably something to think about and read that section of the book. There's also a discussion in the book on chemical reactions. It's very short, but chemical reactions are also going to be described by these chemical potentials. And sometimes they're called electrochemical potentials. So I'm not going to stress that part of it because we're not chemists, but it's still good to understand how that works. So I strongly encourage you to think about that. Okay.
Question.
Good. Yeah.
I've noticed you never really work with these molar units at all. Like
we
the
will.
molar entropy, the molar. Okay, all right.
So when you say molar, you mean like, U
Little
equals U over N.
Yeah.
Yeah. We'll do that a lot when the time comes. Okay. But the thing is, when the mole numbers are changing, it's useful to work in this way.
Yeah, you have to.
Yeah, you have to. You can't use the molar ones here. Okay. And what we'll find is it's much easier to do certain derivations when you're using the molar quantities. So let me erase this just so that people don't get confused as to why that's sitting there for no reason. Okay, good. So now let's think about what we've done, okay? So recall that when we had something at temperature T1 and another thing at temperature T2, okay? We know that heat will flow from one to the other. Okay, and so to determine which way that heat will flow, we can calculate ds, okay? And let's say that ds looks like 1 over T1 minus 1 over T2 dq, okay? So, so if I want to determine which way the entropy is flow, so what I've done here is I've specifically, if you look at the change in entropy, remember the change in entropy is defined by dq over the temperature. Okay, so this first term is the change in entropy of system 1 at temperature T1, And the second term is the change in system 2 entropy, okay? So what I've done is I've just written it out this way. We know that this has to be greater than 0, okay? So if you look at my dq here, the way that I've drawn this dq, the dq is leaving, this system number 2, is leaving system number 2, okay? So that's why I put the minus sign here, okay? So I arbitrarily did it that way, okay? So, so by definition, from this picture, this dq is greater than 1, okay? Because there's an implicit sign here in front of T1, so the heat's going into T1 and leaving T2, okay? So what does that mean about the temperatures? Well, we know the entropy change has to be greater than 0. I defined dq to be greater than 1, so that means that this has to be, greater than 0. So that means that this has to be greater than 0 for the entropy change to be greater than 0. So that means that 1 over T1 minus 1 over T2 is greater than 0. So that implies that T1 has to be less than T2. Okay. Wait, so I got that backwards. No, that's right. T1. So the first term has to be bigger than the second term. And so exactly, that's what happens. Heat flows from hot to cold. Okay. So now let's say that instead of that, we're looking at N1 particles in this system and N2 particles in this system. Okay, and then I'm going to say that the particles are flowing, let's say, in this direction. So this is, dN. So in the same way, I can say, well, ds, by the way I've defined this, I'm going to have mu1 over T1 minus mu2 over T2. dN has to be greater than 0. Okay? Well, based on the signs that I've picked this to be greater than 0, right? So let me just make sure I'm doing this right. And let's assume that we're in equilibrium. So both of those T's are equal to each other, okay? And the way that I've drawn it, the particles are going into U1, okay? So what does this mean? Well, this means that U1 minus U2 has to be greater than 0. So this implies that the particles are going to be flowing into the thing with the higher chemical potential. Okay. So since I don't have a good feeling for chemical potential, let me see if that's what I get. Yeah. So so my notes say matter flows from a high chemical potential to low. So did I get this backwards somehow? Or did I draw my picture backwards somehow? Okay, so let me just look at the equation. So I have dN flowing into N1. So N1 is increasing. So that is positive. So that has to go, so mu1 is greater than mu2. So according to this, it looks like particles are flowing into higher chemical potential. So that's so weird.
I think just the picture is wrong.
The book says that the matter flows from high chemical to low chemical.
Yeah, that's what I think. So someone said the picture is wrong. So I have it flowing from N2 to N1. So N1 is increasing. So
If you have it relative, if you have dN relative to mu2, and the change in particles needs to be greater than 0, so that means particles need to be flowing into it, right?
into what?
mu2.
So the particle should be flowing the other way. So you're saying it should be flowing like that.
And that's how I think you have it set up, because you have things relative to T2 and relative to mu2.
Maybe. This is so weird. Okay, so let me write this down very carefully, okay? Because I promise you I'll think out loud with you, okay? So we know that this let's say this condition holds. Okay, we know entropy has to increase. So let's see what this says, and then we'll draw the picture for it. Okay, so this says if this is positive, then that has to be positive, which implies that mu1 is greater than mu2. Okay, so far so good. So now let's draw the picture for that. Here's system number 1. Here is system number 2. Ah, I found the problem. The problem is, if you look up here, there's a minus sign in the definition here, okay? So everything I've done here is correct, but the point is that the particles are flowing out of the system with a minus sign. So it's true that the particles have to be flowing in that direction. So the particles do flow from high to low, okay? And that's because the partial of S with respect to N is minus mu over T. Okay, it's this minus sign. So that's where there's an extra minus that comes in there. Okay, that's where the screw up was. Okay, and then finally, when I take partial S with respect to V, that gives me P over T. Okay, so let's look at that. So if that's the case, and I have a 2-particle system, okay, so ds is going to be given by P1 minus P2 dV. So here I have a box with a piston, and here's system number 1, here's system number 2. Okay, we know that this has to be greater than 0. Okay, so let's say that P1 is greater than P2. That implies that dV has to be greater than 0. Okay. And if you look at it, this volume change is associated with the P1, because that's the thing that has the plus there. There's a plus here, so it's associated with that. Okay, so that is the change in volume 1. So let me just write it as 1 there. Okay, so what we can see is that volume 1 increases when pressure 1 is higher. It worked. So pressure 1 is higher, the piston moves away from high pressure. So now we fully understand our thermodynamics of ideal gases. The piston will move away from high pressure to low pressure. The particles will move from high chemical potential to low chemical potential. Heat goes from high temperature to low temperature. Okay? It worked. Good. All right, wonderful. So, so that kind of concludes this whole idea of being in chemical equilibrium. Okay? So in chemical equilibrium, the summary is that the entropy has to be an extrema, because remember, entropy increases, so ds has to be 0. And from ds being 0, we get these various equilibrium conditions. And so if we have other parameters, like electric field and dipole moments, we could add that to this, okay? So next, we're going to move on to Euler relations. Okay. Now this, at this point, is pure math. Okay. Now the math is based on some physics. And the physics that it's based on are that U, S, V, and N are extensive. So we're going to take this physics, which has this property, and we're going to apply math to it, and that will give us these Euler relations. Okay? And this is really, really cool how this ends up working out. So what we're going to do is we're going to take U, and U is a function of lambda s, lambda x1, dot, dot, dot. So remember, in our, I think it was our previous time together on Wednesday, we defined this extensive parameter x, which could be volume and number of particles and whatever. So we're keeping it general, okay? So that, remember, because these are all extensive, we can write that as lambda times s x1 dot, 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 okay? That's the definition of extensive. If I take all my parameters that are extensive and multiply by lambda, I'll get, ooh, no wonder you're all looking at me so funny. I forgot to put my u here. Okay. So if I have a function of these extensive parameters and put a lambda in front of all of them, then my u being extensive has to change like this. Okay. Now we're going to use this and we're going to take the derivative with respect to lambda of both sides. Okay. So let me start with the left-hand side. So this derivative is going to be partial u with respect to lambda s times partial lambda s with respect to lambda. Remember, that's kind of the chain rule. Is that what they call it in math? You're going to differentiate with respect to something that's inside of an argument. You differentiate with respect to that function, and then the argument with respect to the variable. Okay, so we get that. And then we're going to get also all the other things. Let me say sum over I, partial u with respect to lambda xi. And then this is going to be as a function of all the extensive parameters. And then partial lambda xi with respect to lambda. Okay? You all agree with that? And then on the right-hand side, that's very easy because the only thing that has a lambda here is this piece. So that's just going to give us u back again. And I'm not going to put all the functional dependence in there. Okay? Are you good with that? Good. Now, the other thing we'll find is that when I take this derivative, that just gives me s, right? And then this derivative here, why it does that? This derivative here will just give me xi. Okay? So when I'm done, I'm going to get a pretty amazing result. Okay? So the first thing, oh, and let me label the other thing here. This u here has lambda s as an argument. So when I take the derivative of u with respect to lambda s of lambda s in here, that just gives me 1 over t. Okay? And then similarly, for these other parameters here, when I differentiate them, okay, they're going to give me something over t. And remember, the intensive parameter associated with x that we used before, we called p. So remember, this p is like a generalized intensive parameter. Okay? So if we apply it now to our one component system, sorry about my handwriting, we're going to get the following. Oh, and I just said something wrong here. I thought I was in the entropy representation. What's du ds? You remember what du ds is?
It's 1 over the temperature, right?
Yeah.
Well, that's what I have, but is that right?
Well, there needs to be a lambda there.
No, something else. Do you remember u? I'll write up here, u equals pds minus pdv dot, dot, dot.
Yep.
So what's du ds?
Yes. T minus B, maybe?
I think that's right, but you're saying it so quietly I can't hear you.
T minus B, maybe?
It's just t,
Just T.
Oh, okay.
right? Because if I differentiate this with respect to this, all I have is t. Okay, so good.
Mm.
Yeah, I heard the t there. Yeah, just, even if you're wrong, just blurt it out. It's okay. Okay, it's not like it's okay. And so here, this is just p sub I. Okay, good. So now when I put it all together, I'm going to get from this side of the equation u equals this times that ts minus pv plus mu n. That's pretty awesome. Isn't that pretty awesome? I find that to be very, very awesome. So we have this relationship, and remember we have du equals tds minus pdv plus mu dm. So we have this, that's sort of where we started with all this, and we derive this. And this is basically the Euler relation. Okay? And then the most general expression for this would be, oops. So if we want to put it in general, and it looks like Callan likes to do this, if you write it in terms of all these other possible things, we can write it like this. Okay. And if we have a multi-component system, then we have u equals ts minus pv plus the sum over mu I and I sum over I. Okay. So depending upon the system, but the point is, it's really cool because this relationship, notice that, let me do this in a different color. These are extensive parameter. It's all extensive. Whereas these guys here are all intensive. Okay. Very, very cool. Okay. So, so we can write it in both of these kind of equivalent ways. And then we can solve for the entropy. Okay. So here, if we solve for the entropy, we have the entropy equals, and we'll have u over t. Okay. And then we'll have my plus p over tv minus sum I to r mu k over t and k. And I guess I should put that down here. And then up here, we would have s equals sum over j equals 0 to r fj xj. This is just a general way of saying the expression below for all the possible extensive properties of the system. Okay. Great. Any questions about that? Okay. Now, I have to admit that when I was taking thermodynamics, my head starts spinning at this point. This derivative with respect to that, integrate this, there's all these variables running around. Okay. But I would just say, look at the simplest stuff. So for example, here, just look at kind of this simple expression and this one, and convince yourselves that that's true. If, and actually even simpler, this one up here, convince yourselves that that's true from this argument here, okay? Because it's a useful relationship that will come in handy, okay? Very good. And then with regards to these generalized pressures, okay, remember that these are functions of S x1 dot dot dot, let's call it x sub t, will be the last one. If we let lambda equals 1 over xt, so we take the very, very last extensive parameter and divide everything through by that, okay? Then what we're going to get is that this p of k is going to be little s, little x1, dot, 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 1 at the end, okay? So we've taken all these things that are extensive and we've turned them into intensive things, and then we've gotten rid of one of the variables, okay? So now we're just going to have t variables, okay? And recall, or you can see here, that this group of variables has t of them, but there's also s in addition. So there's t plus 1 variables there. Okay. So again, I know your heads are spinning when you're doing all this stuff with all these variables, but it's not that bad if you go back and look at where we started. But let me go through and do one more thing. Okay. So let me just do this simple expression right here. So remember, we have u equals ts minus pv plus mu n. And we have du equals tds minus pdv plus mu dn. These are both things that we know are true. We started originally with this expression here on the right in everything that we've done, sorry. And now we've derived this based on the fact that these are kind of first order extensive variables. Now let's differentiate this expression here and see what happens, okay? So if I differentiate this, I get du equals t ds plus s dt minus pdv minus vdp plus mu dn plus n d mu. Okay, now let me take this and subtract that from it. So we're going to subtract those two. If I do that, notice that the u's go away. Okay, and then the TDS goes away, and the PDV goes away, and the mu dn goes away. And all that's left over are these three terms. And so after the subtraction, I'm going to get SDT minus VDP plus ND mu equals 0. So now this is a relationship between the intensive parameters. So these are all intensive. So this relates the intensive parameters. Okay, which is kind of interesting. And to make David happy, if I divide everything by n, then everything will be intensive. I have little s dt minus little v dp plus d mu equals 0. So all is intensive. Okay. And like I said, we're going to use these fairly extensively for all intensive purposes. I just made that up. Isn't that pretty good? Okay.
Yeah, that's pretty good.
Yeah, I thought so. I'm serious, just off the top of my head. So we're done. As usual, I'm perfect. It's exactly 2. But all I'm going to say is that it's useful to understand where this comes from, because it'll be more transparent when we're applying these. But for the purposes of doing the problems, all you need to do is remember this expression. I'll put a circle around it. Remember this expression, and remember that other one up top, which is too far away for me to do. Now this last one that we derived is called the something Duhem. I don't even see where it is here, but I should give it its name. Gibbs. I should remember, he's a well-known guy. Gibbs Duhem relation. Okay, so if you remember Gibbs Duhem, you remember Euler, and you remember du equals TdS minus PdV plus mu dN, you can do everything.